Today we are in week 3 of Algebra 2. Last time you did great in all your assignments in the past 2 weeks. I appreciate that. I hope you'll continue with that. Today we are learning about modeling applications of exponential functions. Modeling or applications of exponential functions in everyday life or in real situation. We are solving different problems. Before that, I want you to recall exponential function is in the form of y equals a times b to the power of x, where a is the initial starting value or y-intercept, and b is the growth factor. Okay, consider y equals a times b to the power of x, which is an exponential function. When b is greater than 1, it indicates increase with growth factor b. When b is less than 1, or especially between 0 and 1, it indicates the function is decreasing with a decay factor of b. So that b is the one which determines whether the function is an increasing or a decreasing one. Okay. For instance, if we have y equals 4 times 1.5 to the power of x, the initial or starting value is, as you see, it is 4. The growth factor is 1.5. Is it a growth or decay? We see that it is a growth because the factor 1.5 is greater than 1. In another way, if you see another example where y is 129 times 0.64 to the power of x, the initial or starting value is the 129. The factor is 0.64. This is a decay since the growth factor, which is 0.64, is between 0 and 1. So that is b determines, when we say a times b to the power of x, the b is what determines whether it's a growing with a growing rate and a growing or increasing exponential function, or a decay or a decreasing exponential function. Okay. Now let's see different examples for this. Before we see examples, we want to bring into attention what are the rates. What do we mean by the growth rate and the decay rate? The growth rate is actually the percentage by which a quantity increases over time. It is what is added to 1 to make the factor greater than 1. If you remember, when we say y equals a times b to the power of x, if this b is greater than 1, we say it is increasing. So it is some rate or some percentage which we add to 1 to make the growth factor to be greater than 1. That is called growth rate. We'll see what would be the general formula to apply or when to use the growth rate. The decay rate represents the percentage by which the quantity decreases over time. That is what makes the function to be a decreasing one, or the percentage of, or the amount we are adding to 1. Usually this percentage is given in decimal, whether we are using increasing or decreasing functions or exponential functions. The percentage is used as a decimal. Okay, exponential growth formula. This is the general exponential growth formula. If b is replaced by 1 plus r, where r is the growth rate and t is the time, a is actually the initial amount. So this is the formula for exponential growth, where we usually use the rate in decimal, usually between 0 and 1. That makes the growth factor to be greater than 1. So some examples of exponential growth are the growth of a bacterial colony, say the growth of saving or debt due to compound interest, the spread of viral videos, and population growth. All these are some examples of applications of exponential function, where we are modeling exponential function to fit real life situation. Okay, likewise, like we have the exponential growth formula, we have exponential decay formula, which is this one, the formula for exponential decay of a variable y at the decay rate r, or percent of decrement r, with time t is given by y equals a into 1 minus r to the power of t, where a is the initial value of y at time t equal to 0. Yeah, when t is 0, 1 minus r to the power of 0 is 1, so you get the y-intercept, or the starting value a. Some examples of exponential decay real situation are problems of half-life of radioactive elements, where we apply our exponential functions formula, or the decay formula. We can use it for that, and also for calculations of depreciation and so on. Okay, let's see practical examples how we are applying whether we are in exponential growth or exponential decay. So our first or second example, already we have taken our first example is this one. So if you have y equals 648 into 1.5 to the power of t, identify the initial amount and the growth rate or percent of increase. Initial amount is obviously 648. Growth factor is 1.25. Where the growth rate should be, the growth rate is 1.25 minus 1, which makes the growth factor to be greater than 1, which is 1.25 minus 1, which is 0.5, or 25% of increase. Look, we represent it actually as a decimal, the 25% of increase. Likewise, this is a growth rate. The 0.25 is a growth rate, and the whole of the function with 1 plus 0.25, which made it 1.25, this function to be increasing. We use it for a growth rate examples or problems. Likewise, if I have y equals 648 times 0.45 to the power of t, the factor is 0.45. So to find the decay rate, we subtract from 1 that factor, which was 0.45, and then we'll get the decay rate, which is 0.55, or 55% is the percent of decrease, or the decay rate for this given function. Now we'll see other examples where we apply the growth rate or the exponential function as a growth rate or decay rate. The first example is this one. Since 2015, college tuition rates have increased by about 5% per year. If college tuition originally cost $20,000, how much was the college tuition in 2018 from 2015? And how much will college tuition be in 2025? Okay, examples are usually hypothetical. They doesn't represent a specific college, just for the purpose of example. Let's do this problem. So the initial amount A is considered as the 20,000, which is in 2015 what the college tuition fee was, and then the time is 2018 minus 2015, which is 3. The growth rate R is given to be 5%, where 5% mean 5 over 100, which is 0.05. We are using this in our formula. So y equals the a, which is the initial amount, 1 plus r to the power of t is our formula. So we are replacing the appropriately values. For a, we replace the 20,000. For r, we replace the 0.05. For t, we are replacing the 3. Then this would be just 20,000 into 1.05 to the power of 3. For this, we can use any or graphing calculator or scientific calculator. Sometimes Desmos, for sure, Desmos has an inbuilt calculator. You can use that too. So what I would do is I place 20,000, which is the initial amount, times the 1.05 to the power of 3. Remember that the inverted v lets me to write the exponent. So this is what we get as our result. In 2018, college fee would be 23,152.50. Okay, so the question was, for the question A, how much was college tuition in 2018? So for A, in 2018, college fee was 23,152.50. Okay, this is our example or the answer for question A. Question B, how much will college tuition be in 2025? It says. So the time will change now, because in 2015 it was 20,000. We are going to calculate or to predict what will it be in 2025. So the time will be 2025 minus 2015, which is 10 years. So the only difference from the original example is changing the time from 3 to 10. It's not only between 2015 and 18, now it is between 2015 and 2025. So the initial amount remains the same and the rate is the same. The only difference is 10. Okay. So what we do is, sometimes if you want to really use the original function or the original keyed amount in the calculator, we can go back with upward arrow and then enter. So I can go back and replace this 3 by 10. This will make it just the answer for 2025, how much college fee would be. So I get this value to be 32,577.89, which is in fact can be 90. No, it should be 89, because 2 is less than 5 there. So how much will college tuition be in 2025? For the answer for this, college fee, or tuition fee actually, college tuition fee will be 32,579 and 89 cents in the year 2025. So exponential functions, or especially when they are growth rates, can help us to predict, or sometimes even the decay rate, to predict the future amount. It can be a population, It can be questions like this: what would be tuition fee in the long run? Okay, let's take another example. Example 3. This is our third example. You bought a car, say for 16,000. You expect the car to lose value or depreciate at a rate of 11% per year. Write an exponential decay model to represent this situation and find the car's value after 6 years. Okay, to do this, we are using the exponential decay formula we already established. Let me demonstrate this. The formula we are going to use is y equals a into 1 minus r to the power of t. Now this is an example of a decay rate where a car which was bought at $16,000 or 16,000, and the rate of decrement is 11%. 11% mean 0.11. So the time is given as 6 years after it was bought. So we are just plugging in these values: 16,000 into 1 minus 0.11 to the power of t, where t is 6. This is what we are going to figure out. So y equals 16,000 into 1 minus 0.11 is 0.89 to the power of 6. The same way we did in our previous example. You can put this into our calculator, whether you are using graphing or scientific calculator or the inbuilt Desmos calculator. Okay, so 16,000 times 0.89 to the power of 6. This gives 7,951.70. So find the car's value after 6 years. It said the car's value after 6 years is 7,951.70. As I said, the examples are just hypothetical to do problems, and so the car which was bought for 16,000 its value will go down to 7,951.70 after 6 years. Okay, so let's take our fourth example. The fourth example is this one. This is a compound interest problem. Suppose Mr. Peter saved $1,000 in a bank account that gives 6% of annual compound interest. Find how many years it requires for his money to triple. Recall that R, which is 6%, means 6 over 100 or 0.06 is the rate. Okay, here the initial amount is 1,000. The factor will be B, which is 1 plus R, 1 plus 0.06, which is 1.06. Since the final amount should triple from 1,000, that's what we want to figure out the time it takes. His saving, which was 1,000, becomes 3,000. So we need to find the time t when the saving is tripled. The equation is just 1,000 into 1.06 to the power of t. You don't see maybe this very small there t, but to the power of t should be 3000. So we'll find t that gives y equals 3000. One easy way to do this is to use to enter or to key in the function y equals 1000 1.06. Let me just demonstrate this. The function given is 1000 into 1.06 to the power of x. Let's replace the t by x. We want this function value after certain years to be 3000 so that it will be tripled. What we do is one simple way, even though we can use graphing of making this equation with y equal to 3000, find the intersection. The easiest way is to use table feature. If you use the table feature in the graphing calculator, we can easily determine the closest amount to 3000 by entering that into the calculator to the y. I already entered this value earlier, which is 1000 times 1.06 to the power of x. So I go to the table feature, which is second and graph. It gives me all the values for different x values. For this x values, what would be the value of the function or of y? For instance, if we take when x is 0, when x is 0, I see that y is 1000. So the main thing is to find after certain years when will x be, y will be 3000, or for what value of x will y be 3000 is the question. So I go on the y until I get 3000. So if I proceed to 2540 for 16 years, 1692 for 17 years, and so on. It goes on. 18. When you are on 19, you get, which is 3025 and 60 cents. This, okay, 3025 and 60 cents. That's what I see. So this is the closest number to 3000. So when I see this is when x is 19. So the many triples, find how many years it requires for his money to triple. I can say his money will triple. So his money will triple in 19 years. So the amount which was 1000 with a percent rate or growth rate of 6% will be 3000 in 19 years. So these are the different examples for applications or modeling exponential functions. We have seen the growth rate in terms of this type of problem in compound interest, or correlate tuition fee increasing through years, or depreciation, which is the car's value as it depreciates through years with a certain decay rate.